Hello, everyone, and welcome to the Siemens Digital Industries Software webinar. Now I'd love to introduce our presenters. With us today, we have Dave Walker. Dave is a Senior Technical Product Manager with Siemens Digital Industries Software. And joining us also today is Greg Arnott. Greg is the Product Marketing Manager with Siemens Digital Industries Software. So, gentlemen, welcome to today's event. And with that, I'd like to pass things over to Greg to get us started. So go right ahead.
Thank you very much, Kitty. It's great to be here. Welcome, everyone, to From Chaos to Collaboration. My name is Greg Arnott. I'm going to be joined by my colleague, Dave, who will take over in a few minutes. And I can assure you that we are totally live here for you today. We're going to be covering quite a lot of interesting material. But before we get into that, I'd like to pose a little question. If you can imagine, if you were a mechanical engineer and imagine that you've just made a design change. So does the PCB engineer in your company, in your organization, does he or she know what you've done after you've made that design change? Because while our industry research shows that interdisciplinary collaboration in product design is often very good, and we know that from a certain amount of primary research that we do, sometimes it isn't so good. And sometimes collaboration between electronic and mechanical design teams, it just doesn't happen. Instead, it can be chaos. Engineering teams are developing independently, and it's not until the final system integration that we discover that what we'd designed, it overheats, it doesn't fit, and possibly it can't even be manufactured. It can even be built. So we invite you to join us in this webinar where we're going to show you how to go from chaos through to collaboration. But in the meantime, hold on to that thought. Does the PCB engineer know what change you just made? All right. The next button works. That's great. Okay, so while you're thinking, let's talk about some trends. I always like to kind of look at the very latest and greatest as what is happening in the industry. Obviously, AI is a huge topic. We're not going to talk about that too much today. We're going to have another webinar coming up later in the year that will address that more fully. But I'm going to talk about some of the latest trends in electronics development globally and their implications for you and also for us. The first of these is going to be Edge. The title here is Smarter Devices, Smarter Living. But AGI is referring to the deployment of artificial intelligence algorithms and processing capabilities directly onto edge devices, allowing real-time data and analysis and decision-making at or very near the source of data generation, rather than relying on centralized cloud computing. So a little bit the opposite of these LLM modules that nearly always have to send your words off somewhere. So for example, like real-time translation, there are things like earbuds that now, and I didn't believe this was a thing, but it is. You can get earbuds that offer instant language translation without any kind of internet connection. And your facial recognition, your smartphone. Smartphones these days, they feature the faster and more secure facial recognition, improving the device security and the user convenience. And this offline functionality, which is a characteristic of AGI, it enables devices to perform complex tasks without even having that internet connection, which is tending to promote reliability and accuracy and reduced latency. The on-device processing associated with AGI minimizes delays, and it provides a more responsive and a seamless user experience and improved privacy. Because your data is being processed locally, it reduces the need to send sensitive information to the cloud, which is inherently giving you more privacy. So examples of systems that are AGI, obviously systems like ADAS, Advanced Driver Assistance Systems, and autonomous driving are examples where it's better to do the processing at the edge. Both of these rely on processing vast amounts of sensor data in real time directly on the vehicle rather than sending the information to the cloud. And this allows for, indeed, it's necessary to have faster decision making and response times, which are critical for safety and efficiency in dynamically changing environments like driving a car. And in an ADAS, AGI is used for features like object detection, lane departure warning, and automatic emergency braking. And for autonomous vehicles, AGI processes data, lots of data from cameras, radar, LiDAR sensors to navigate and respond to traffic conditions without needing to send data to the cloud for processing. So, the cloud is a great thing, but AGI is kind of an interesting development at the moment. A significant implication of AGI is that more processing power will be required locally on devices, so it's good for chip companies, and that's because, as you can imagine, Edge AI involves running complex AI algorithms directly on these edge devices. And the shift towards this Edge AI AGI will drive demand for more capable and efficient local processing, influencing both hardware development and software optimization. And this trend has implications in terms of needing more powerful local processing. It has implications in terms of the energy consumption locally, the management of that heat, the thermal issues there locally, security in terms of the physical access risks and sensitive data being processed locally. Then I got a couple more to touch on briefly, which kind of Siemens has more of a story to tell there with the next two we're going to look at. So, you know, the rise of flexible and rigid flex within electronics systems and enclosures. Flexible electronics, they can mount components on flexible substrates for bending or shaping, while rigid flex PCBs combine rigid and flexible board technologies for versatile applications. And some of the benefits of rigid flex are space savings and miniaturization. Rigid flex PCBs enable compact designs by replacing connectors and wire harnesses, important for space-constrained applications. Enhanced reliability, there are fewer solder joints and connectors, that means fewer points of failure, leading to better and extreme environments, and design flexibility. These things can bend, they can twist, they can fold into complex geometries, allowing for innovative product designs in wearables and medical implants. And versatile applications, from aerospace and avionics to automotive ADAS and implantable medical devices, rigid flex PCBs are revolutionizing industries. The rise of flexible and rigid flex electronics is transforming industries by enabling the creation of more compact, reliable, and adaptable products. This shift is not only driving innovation in sectors like aerospace, automotive, and healthcare, but also opening up new possibilities for wearable technology and medical devices, ultimately enhancing the user experience and improving product performance across various applications. This happens to be an area where Siemens has very capable software product offerings. NX, for example, allows for the design of both rigid and flexible printed circuits, enabling the creation of complex electronic systems that combine the benefits of both technologies. All right, sustainability, it's always up there these days. And sustainability in product design it's not just creating products sustainably, well, that's a good thing, but it's creating products that will be sustainable themselves throughout their useful lifetime and then can be disposed of sustainably at the end of their life. If you think of factors like sustainable materials, using eco-friendly, recyclable and biodegradable materials in product design to reduce environmental impact and promote resource conservation. Then you want to be energy efficient. Implementing energy-saving technologies and optimizing product efficiency helps lower energy consumption during the operation of the device during its lifetime and ultimately reduce its carbon footprint. Then when you're at the start of a product, you've got to think about the end of life of it. Design for disassembly, creating products that can be easily disassembled at the end of their life cycle, like not having glue and kind of connectors that are going to be wasteful, facilitating recycling and reducing waste in landfills. Then the ability to do life cycle assessment, conducting comprehensive evaluations of a product's environmental impact throughout its entire life cycle, from raw material extraction to disposal. And circular economy principles, adopting practices that emphasize reusing, refurbishing, and recycling products to extend their lifespan and minimize resource depletion. As sustainable design practices become more prevalent in electronics, we can expect significant reductions in environmental impact, leading, I hope, to a more circular economy where resources are conserved and waste is minimized. This shift will not only benefit the environment, but also drive innovation. It will improve a brand reputation and enhance customer loyalty, and will, I hope, transform the electronics industry into a more responsible and sustainable sector. Siemens NX plays an important role in enhancing sustainability by integrating environmental impact assessments early in the design process. Through its Sustainability Impact Analysis module, NX enables designers to make informed decisions based on comprehensive environmental metrics, allowing them to optimize material choices and substantially reduce environmental impacts, thereby supporting broader sustainability goals across the product lifecycle. All right, that's enough for me at this point. I'm going to hand over now to my colleague Dave.
Thank you, Greg. So, yeah, lots of information there. And I think the bottom line of all of that is products are getting more complex and need to be tightly packaged. And the way we address that is to make sure that our domains between the electronics and the mechanical world are actually better integrated. So we asked a question at the start: how do we go from the chaos of not knowing what's going on and moving into a regime where things are understood and everybody has visibility? So if we do remove the chaos from the process, and I talk about chaos as emails, conversations, screen grabs, post-it notes, we need something to replace it that we can rely upon. So we're introducing EDMD Exchange. But what does that actually mean? EDMD Exchange refers to the collaboration process between disparate domains, in this case, electronics and mechanics, MCAD. You may have moved on from emails and screen grabs and using historic basic methods such as IDF, but you want to go further, really embrace the connectivity between domains. At the basic level, you have the exchange of the board geometry and component positions. Usually the components are represented by solid blocks. We refer to those as 2.5D blocks. Maybe you want to see the copper traces on the mechanical side. Take the example of a Bluetooth antenna. Simple copper on the surface of the PCB that's so important to make sure no mechanical components obstruct it. Wouldn't it be great if you could see it while designing the housing? And then 3D models visible in both domains, true representations of mechanical parts in ECAD and electronic components in MCAD. So we have it all, right? Okay, but how does it all fit together? You then need the ability to run clearance checks between everything. Standard clearance checking won't cut it for copper traces. They're part of the board. So we need a PCB-specific interference check that understands the anatomy of a PCB and surrounding assembly. Wouldn't it be great if I could run a design check between a copper power plane and a mechanical component like a screw or metal bracket? Each area lacking in capability can be the cause of the dreaded PCB respin. I read an independent report a few years back that claimed the PCB respin could run into millions of dollars in delays, costs and delayed projects and so on, taking material and time delay into consideration. So let's start with the basics. The board profile, components, holes, keep outs or restriction areas, however your language you prefer. Add the next layer of capability. Do I have the components the right way round? In one identification, for example. Who owns the various components? Do some components live together as a group? Now we add the copper traces, including vias and blind vias. What about solder mask and silk screen? Think of the Bluetooth antenna situation I mentioned earlier. Have you ever designed a PCB only to find the corner of a shield is lifted on one corner by the solder mask, destroying the grounding effect? Let's not stop there. Let's consider embedded passives and RF components. We're into high density packaging now. The Bluetooth antenna I spoke about earlier comes into this area. Do your boards have high density packaging features like cavities and of course wire bonds for microelectronics and power solutions? But it's not just about rigid boards. Enter the realm of flex and rigid flex, as Greg mentioned earlier. Does your collaboration solution understand flex bend areas, stiffeners, adhesives, and complex rigid flex boards, stack-ups? To realize a true digital twin for collaboration between domains, both need this high fidelity visibility. So I'm going to take you on a little journey through a typical collaboration process so you get the span of what's going on, and then we'll dive deeper later on into some real-life demos of the actual process. First, we define the board outline. Usually it's recommended that this is done in the MCAD side, but it doesn't have to be. We add the electromechanical components. Generally, these would be those components that define the board interfaces to the product assembly, the enclosure, the connectors and the like. As it's typical design in context, the product assembly already exists, defining the interfaces and constraints for the board. Now it's time to collaborate. We send a baseline to the ECAD domain and bring along the mechanical components for full visibility in that ECAD domain. The layout designer will add the electronic components defined by the schematic and propose these changes back to MCAD. The mechanical designer now reads these changes, decides if they should be accepted or rejected, and sends back a response of this decision. This part of the process can iterate a number of times until the final design is agreed upon. Iterate now rather than board respin. Once agreed, the final copper traces can be laid down and sent to MCAD. That's the full realization of the design in both domains. Greg.
Thank you, Dave. All right, thank you. So what we're going to do now is take you through a number of different design stages and step through these, starting with the board geometry. And as we go through, we'll reveal what each of the other steps are, but all the while following the process we just saw. Nice animation here. What we're going to do through now is take you through a number of demonstrations. And before we jump into that, let's start with the board geometry as the first step there. So we've got a pretty comprehensive list in terms of the things that we can collaborate on. The board profile, the thickness, the cutouts, and so forth. So there's a lot of capability within the generic design of the board that we can define here to make a very rich data set. You'll notice at the bottom there that we've got flex and rigid flex definition, where we can really define on the mechanical side the true mechanical profile, outline, and thickness, including the stiffeners and adhesives of a flex or rigid flex design before we proceed. So our first demonstration is going to be about how to create the board geometry. So let's have a look at that. Dave, it feels like time to see this in action.
Fantastic. Thanks, Greg. Okay, so yeah, let's create the board and see exactly what we're going to do there. So what I've got here in NX is a top-level assembly and a board, which is one of the components within there. And I make that the work part, and we can work into this particular area. I've created the board profile just using a sketch, and it's got a cutout and a few other features in there. And we just generate a thickness for this board. We pick the area, we define the thickness, and putting this in the negative Z direction, we want the datum to be on the top surface of the board. Next step, let's put some mounting holes in there. So once I've got a definition here, what I've created is actually linked points from the enclosure. Obviously, you can't see the enclosure in this particular design. And I just generate the hole features for each of those mounting holes. And once those features are complete, we can then start to look at how we tell NX about the aspects of the design for the collaboration. So the first thing we need to do here is to define the board profile. So what we do here is something called tagging. It's an attribute that's added to the geometry. We pick the coordinate system, which is the orientation that the ECAD designer will see it. And I go on to do the same thing for the holes. I can pick the holes up en masse. I don't have to do them one at a time. And these are non-plated holes for the mounting to the enclosure. So what I've also done here on the next step is that I've generated a couple of sketches, and these represent some no-go areas, some restriction areas, some obstructs, depending on your preference in terminology. And we define these as an area. So I've got a placement obstruct here, which is to prevent any electronic components being placed in that area, and that's communicated to the ECAD side. I've got a separate area here, which is it's a special area, and we do some name alignment. And I've got a user draft layer 1, which is a name match to a special area on the ECAD side, such that the ECAD side can understand what to do with that. Greg.
Thank you, Dave. You know, watching that there, it really strikes me how easy it is to get your build geometry ready for collaboration. So now we're going to go into the next section, and this section is going to be about the component exchange side of things. But what does component exchange actually mean? Over to you, Dave.
We talk about it, sorry. When we talk about exchange, it can mean many things. So let's dig a little deeper. Electronic or ECAD components, so that's ICs, resistors and the like, that's clear. Mechanical cells are a special case item that have a 2D definition that ECAD designer sees. We then have assembly models which can be pushed across to the ECAD world, and we'll see that later in a demo as well. It gives huge benefits when checking the design for issues on the ECAD side, and so on through the different capabilities to the final one there that's about understanding PCB variants. In the electronics world, PCB variants are clear for different component fits and do not fits, but to see that on the mechanical side is something truly impressive, and that's something we can also support there. So let's look at a very simple example of placing ECAD components. So this is the board that we prepared earlier, and it's typical for the MCAD user to place components that interface with a mechanical enclosure and other system components. Using the add component command within NX, in this example, we know the location of the connector specifically, so we can dial in the coordinates. But this doesn't have to be the way that it's always done. We can use constraints and alignment to other mechanical items around. Similar to the board and the holes and the areas, we can define the attributes, telling NX and Expedition what this particular component means. And we define the reference designator as defined on the schematic. We can define ownership to prevent the wrong person from moving it. Package cell outline for clearances can all be added here. And we repeat those steps for each command. There are more automated ways of doing this when the BOM is uploaded to Teamcenter in a managed environment, of course. So on to component placing assembly models, sorry. So we mentioned about the mechanical components earlier. So we've taken that one connector and added a number of other connectors, and we've got a heat sink there in exactly the same way and identified them. Now we're going to place the mechanical objects. Now, depending on the design constraints, they will already be in place and the board will be dependent on them. But in this particular design, the front panel is attached to the PCB as it runs in on a card guide. Now, there's no need to add any attributes to the mechanical. NX understands what to do with them and will transfer them to the ECAD domain. Back to you, Greg.
Thanks for that, Dave. So we've dug a little bit into detail now in terms of the board creation and how we transfer electronic, mechanical, and even the assembly components between the two domains. But Dave, how do we make sure everything's all in sync as we go through from one side to the other?
Right, so let's review that collaboration workflow. The data is synchronized in a process we call co-design. This is a conversation between the two domains using a process of IDX collaboration files that track the history and provide a way to compare and update the design as it evolves. The workflow is truly bidirectional, with a concept of baselines to mark the start of the design, followed by proposals and responses as engineers talk to each other through the process of accepting and rejecting changes. With the ability to control ownership, the responsibility for separate aspects of the designs are made clear. And if we dig a little deeper into the Siemens capability, placement groups, for example, are understood in the ECAD world. However, NX is the only MCAD tool capable of understanding and collaborating on this concept. So let's go ahead and create that baseline as we move forward. We'll take the assembly that we prepared earlier and we'll create the baseline. We choose the file format, the file's name and location, which can be in a managed environment, but here it's just in a native system. And we'll add the option to send the mechanical components. And once complete, the information report can be viewed for successful publication of the data. So we're now going to switch across to taking that baseline information and viewing that with inside, in this case, Expedition in the ECAD world. So switching gears to ECAD domain here and take a look inside Expedition. Using the MCAD collaborator, we can see the contents of the baseline file and review that content. So here we can see in the preview, I can preview the board profile with its image. I can inspect individual components and look at their structure and their definition for each one of the components, the board, the mounting holes, and so on. And this gives us a good insight into the overall design. And when it's applied, we can now see exactly what we had on the MCAD side in the ECAD side. And the baseline communication is complete. Now, we spoke about the mechanical components a little earlier. This is done as a slightly different step. And the way this is done in Expedition, we load the mechanical items using a load assembly command. When we exported the baseline, we generated this mapping file that says these are the components that you need to introduce into the ECAD world. And you can see there's no moving around or placing or importing of files. We can manage the visibility of those with the assembly manager within Expedition, and this gives the user the ability to do 3D design rule checking right there on the actual 3D geometry. So I'm going to carry on now, and what we're going to do is to, on the ECAD side a little, the hard work starts here for the ECAD designer, where he needs to place the remaining electrical components. And they're placed according to the design. And in this quick example, we'll place just a few components rather than the whole design. Once ready, we can then send a proposal back to NX. And remember, only the changes are sent, not the complete design. The designer chooses what to send to, and they wait for a response, or they can continue placing the design if this is an interim send of the information. Well, once that proposal has been sent, we jump back into NX, and it's simply a case of bringing that proposal file and reviewing the changes. So when we read that incremental file, we choose the appropriate file. You can see there are board changes, and that's probably due to the layer stack information coming across and changing the thickness. And then we've got all the components, which can be individually accepted or rejected. We're going to accept all of them, pull them in, and you can see those components now. And what we've done is we've sent a response file back across to Expedition, who then need to apply that response file to say, I accept that you've received the data and we can now move forward in the process. So we can see in Expedition here, the response file, all of the check marks says the mechanical engineer has accepted his proposal. And once that's applied, the two domains are back in sync and the process can iterate from there. Greg.
Thanks very much, Dave. So hopefully you've seen what we've been talking about here in action right the way through the presentation today. Having the electronics engineer in Expedition being able to see the full mechanical assembly, and if that mechanical assembly changes throughout the design process as that clone assembly data is moved across, it gets updated within Expedition so both sides are in sync. The engineers have the capability to see the changes and keep the design on track. So moving on to our next segment, we're going to talk about copper transfer. But what does copper transfer actually mean? Back over to you, Dave.
Thanks, Greg. Okay, so up to now we've been talking about board profiles and holes and restriction areas and components. But what about the other content? NX and Expedition can collaborate on an extended set of object types, some of which are included in the industry standard IDX capability, and some have been layered on top by the Siemens solution. It's not limited to just copper though. Solder mask, cover lay for flex and rigid flex, silk screen, and even wire bonds, as I mentioned earlier, can be added to the collaboration item. Let's take an example. Let's take a look at copper trace. collaboration between NX and Expedition. So we're going to start on the Expedition side. And what we do is we define the objects to collaborate with. In this example, we're back in the MCAD Collaborate, and we load a different scheme, and we choose the external ADX capability. And we can see we've just got copper items, the traces, the pads, and the vias on the outer layers. And these are sent using the external file type across to NX. So what we do in NX is that we read that information in.
Alrighty, so we've gone through the whole process now in terms of the collaboration of the board, the components, the mechanical components, and even now down to the copper traces. So let's just jump into our last segment here and take a look at some of those advanced capabilities.
So when we talk about advanced data exchange, when we bring the two domains together, it's not just about collaboration. Although the process of seeing the design truly replicated across both domains is a long way from the chaos we once experienced, we can go further by looking at different aspects of the design. Electronics generates heat. Greg mentioned this earlier. That's physics. So we have an integration to NX Flow EFD for the thermal simulation and analysis. The data we need is provided by the collaboration process from both NX and Expedition. We don't need to create any new data. We just use what we've already got. I briefly mentioned wire bonds earlier. This is another advanced collaboration item. It's a three-dimensional challenge. Clearly replicated across the domains by our solution gives great visibility. And of course, the advanced capability we have in Flex and rigid Flex collaboration is unrivaled and continuing to develop as we work with our key customers. What about manufacture and documentation? The typical output for PCB manufacture is now mainly ODB++ format that the ECAD tools generate. NX can read these files and create the full representation of the panel design in NX for validation, and of course downstream use. For example, jigs and fixture design that's pertaining to the panel rather than just the individual PCB. And we're not stopping there. The Siemens solution is ever evolving to cover a wider range of requirements. Greg.
Thanks, Dave. So if I just wrap up the session, I think what we've seen today is the powerful integration between the mechanical and the electronic domains that is truly seamless with the Siemens solution there. We can benefit from the efficiencies of the conversation between those domains and reducing the cycle times, and more importantly, reducing the respins. We're sharing data to reduce design costs. So streamlining the collaboration between the two domains brings a much faster, streamlined method and process, and really gives an insight in one domain about what the other domain is doing right now. And that's important, being able to have a single team working in different disciplines. And then improved intelligence, the system architecture and integration and the analytical capability between the portfolio of solutions really takes away any concerns you might have and worry about, well, are the tools really doing what we want them to do? It's important that these tools do the job that they're supposed to do, and that they support the design process, and that you're actually succeeding in getting the products out the door by reducing risk. And as it says, there's real-time decision optimization. Multi-domain collaboration is an area that Siemens is really focused on, and we've been continuously updating. So you'll notice not just now, not just today, but in the future, you'll see more and more features being released to help designers through these traditional bottlenecks and help you get ever closer to a seamless collaboration. We're just about at the end here. So thank you everyone for watching. Done very well to make it through to this slide here. If you have any questions or you'd like to request more information about our solutions, please feel free to reach out to us and we'll get back to you. If you would like to get hands-on with NX right away, just use your camera device to scan the QR code on the screen there and you can start your free trial of NX today. Alternatively, you can always shortcut to us real quick, just easy to remember, siemens.com/NX. what other URL would you ever want to type in? You can also make use of the resource lists to the side to find out more about NX and Expedition. And if you have a couple of seconds, please do take the time to fill out our survey. Now, Katie, I'd like to hand back to you.
All right, great. Thank you so much. So, great presentation, guys. As I mentioned, we have time for some questions. Audience members, there is a Q&A window just below the bio in your view there. If you'd like to ask a question or make a comment, feel free to type into that window and click submit. All right, gentlemen, moving to our questions. First one I'm looking at here. Does the ECAD or MCAD or ECAD collaboration process described in this webinar work with all ECAD and MCAD tools?
Right, okay, I'll grab that one, Katie. Yes and no. Methodology, the EDMD exchange process is based on IDX. And the IDX process is an industry standard, is subscribed to by each of the individual tools. So Siemens NX, Siemens Expedition are compliant with the latest capabilities in the IDX standard, as are some of the other tools out there. But it is really dependent on the individual supplier, software developer's capability to comply with that standard. So NX works well with ECAD tools that are compliant with that standard, and Expedition works well with MCAD tools that are compliant with that standard. So it's a bit of a yes-no answer, I'm afraid. It really does depend, but do reach out if you have any specific questions on that one.
All right, great. Thank you so much for that answer. All right, just looking at the queue here. This person is asking, is it difficult to change from using IDF to IDX? What's involved?
Okay. Hey, Katie, I'll go for this. I can't let you have all of the fun. I'd say from a user perspective, the change can be pretty transparent. It can be completely transparent. An IDX baseline transfer basically mimics an IDF transfer. So if you're just using baselines, the user would see no real difference. There's nothing to learn. The user would just use the new format for collaboration. Once implemented, users can then progress on from there to start using incremental exchanges with the full, that incremental kind of functionality, full accept and reject capability per change. So yeah, it's not that difficult to change.
All right, great. Thank you so much for that answer. So just a reminder to the attendees, if you have a question today, use that Q&A window and grab those resources while you're watching. All right, gentlemen, next one here. You noted that design complexity is increasing. Doesn't that imply that ECAD collaboration is becoming increasingly difficult to achieve?
Right, so good question. When the products become more complex, and we spoke about high density packaging with embedded passives and cavities within boards and flex and rigid flex, yes, the collaboration process becomes more complex. But in terms of difficulty to achieve, it really depends on the tools being used. So speaking from obviously the Siemens perspective on this is that we develop both sides of the collaboration process, both MCAD and ECAD, and our development and planning teams and product management teams work very closely together to make sure that we are identifying the new complexities and providing solutions for them. Now, if you were using a mechanical tool from one supplier, an electronic tool from another supplier, the alignment of those tools may take one or two releases to catch up before they're compliant with each other. So in terms of, is it difficult if you're using tools from different suppliers? Probably yes. If you're using tools from a single supplier that combine and track their development process, it becomes a lot more reliable to use that.
All right, thank you so much for that answer. We've got time for a couple more here. This one is asking, which ECAD tools can NX work with?
I'll grab that one again, actually. Thanks. Obviously, Siemens Expedition. We have a very good integration using the ADX standard with Cadence, because Cadence Allegro is compatible with is up to date with the IDX capability. We have a specific integration with Zuken CR series, or design, apologies for getting the latest name, but CR5000, CR8000 series products from Zuken. We do have a specific file format for them, but I know they're working on improving their IDX capability. A very common product is Altium Designer. We do collaborate with them. However, their compatibility to IDX is not fully up to date, so we recommend just using IDF when collaborating with Altium Designer. And again, any others that I haven't mentioned, it really depends on their collaboration capability in terms of IDF and IDX standards.
All right, thank you for that answer. So looking at the queue here, we've got one more question left in our queue. So if anybody has any last minute questions, now would be the time to ask those. So gentlemen, last one that we have today, unless we get anything in here. Can NX interpret rigid flex designs?
Yes, absolutely. I'm just going to switch back to this slide here and just skip through to this area here. So we've got a pretty complex rigid flex design here. The copper traces can track through. We can define the layer stack of the rigid flex. And what's really important, NX can generate the layer scheme from a corporate standard or a definition and generate the true thicknesses for rigid flex, flatten them out into what is typical for the ECAD user to see, and push that across through the collaboration process. So interpreting designs coming, if you have a rigid design flex from Expedition or from another ECAD tool and bring them into NX, we have some import capability and alignment tools that enable us to do that also. So absolutely, yes, we're good to go on rigid flex designs.
All right, thank you so much for that last answer. So we don't have any more questions left in our queue, gentlemen, but if any attendees feel like asking any questions following today's webinar, that is definitely an option. So feel free to come back and ask anything if you think of it after today. So at this point, guys, we're going to start to wrap the webinar up. I want to say a huge thank you to Dave and Greg for such a great webinar with great demos and for answering some of our attendees' questions. So gentlemen, thank you so much.
Thank you.
It's been a pleasure. Thank you, Katie.
Cool. So again, thank you all for taking time to attend this webinar event. Take care, and we will speak with all of you soon.
Thank you for watching. To learn more about this topic, check out the links in the description. And if you enjoyed what you saw, like the video and subscribe to the channel.